about distributed probabilistic strategies in a moment.
Okay, thanks very much. And I was thinking about something nice to say about Prakash, as one does on these occasions. And I remember something very nice that Neil Garney once wrote on Facebook on it. He said, "You're like a burst of sunshine." And we need that today with all this bad weather. And so I've got you some sunshine in a bottle. Wow. That's so you're very well. So you like it anyhow? I'm sure. So I'm going to be talking about distributed strategies and how to make them probabilistic. And relate a little bit to what Gordon's been talking about, in that it will be concerned with mixing probability and non-determinism. So I've been concerned with generalizing domain theory, and have stumbled across these distributed games and distributed strategies as a way to try and do that. And in going to this more general framework of concurrency, as sometimes happens when you become more general, it begins to illuminate the situation more clearly and shows, in fact, I think, that a kind of more new mathematical robustness to the notion of strategy. In particular, the strategies can be viewed as special kinds of profiles. But I'm going to be concerned with extending the language of strategies that's come out of the model to probabilistic strategies. Oh, that's right. So, talking about event structure, what we're going to be doing is following this program of replacing trees and forests that they usually use to describe the behavior of games and strategies by event structures, which are these kind of concurrent analogues of trees, in which you have events and you have causal dependency on them and consistency, and this gives you, and they satisfy some reasonable axioms, and then one, oh dear, going on there. Then one from this gets the notion of state, configurations and event structure. Events you can see at some stage in computation, and they're naturally enough just taken to be consistent with downwards closed. Okay. Now, so I'm trying to get some basic material on the event structures out of the way that Prakash knows very well. Going back about 30 odd years now, there's some fairly well established maps on event structures. They're a map from one event structure you know with a partial function on the underlying events. It sends a configuration of the domain event structure by direct image to a configuration of the codomain event structure, but in a kind of locally injective way, this way. And this will make sense when we come to look at games and strategies in a moment. But it's important that one has this extra condition in that it's a kind of respecting the events condition. In fact, we'll touch on a slight generalization of this to affine maps, in which see, these maps will always, by nature of being acting on configuration by direct image, you're going to take the empty configuration to the empty configuration. We sometimes don't want that. We want to sometimes go somewhere else in the event structure. So we'll look at a little bit at affine maps. They'll come in later. Okay, so the basic program is to try to develop games and strategies using these event structures instead of trees. So we represent the behavior of a game by an event structure in which we tag the events by plus and minus to signify whether they're a player or opponent events respectively. Given that, we've got simple operations that we'll use on these games. We've got parallel composition of event structures, just got by juxtaposition. We can do that very simply with event structures. Then we have, these are two-party games, then we have a notion of dual game where we just reverse the roles of player and opponent. Okay, so that's how we represent a game, or the behavior of a game. So what's a strategy in such a game? Well, I won't answer that directly, but I'll first say what a non-deterministic play in that game is. So that's like a history of the moves that can actually occur in such a game is. Well, the game represents the possible moves that you can make with their causal constraints and consistency. And then we want to have another event structure S here that's representing the actual moves that are made in the play itself. They will also be subject to certain constraints, and they will also be moves, so they'll be tagged by pluses and minuses, just like the events in the game. But we want to somehow have that the actual respect the constraints of the game. And this is where these morphisms of event structures come in. We're going to take such a non-deterministic play to be a total function from the actual play to the possible plays of the game. So the actual play is represented by S, and the possible plays are represented by the event structure represented in the game. And this will mean, for example, that because of the nature of configurations going to imaging numbers configurations, a position of play, a state of play in the game, configuration of S, will go to a position in the game, namely a configuration of A. And moreover, this local injectivity condition means that you can't play a move more than once. An occurrence of a move can only occur once in any action. So then we want to make a bicategory out of this notion of non-deterministic play. We want some notion of strategy, and they're going to be some kind of special non-deterministic plays, and we're going to have a rationale for choosing what that special actually means. So a strategy in a game is going to be a special non-deterministic play, and a strategy between two games, from a game A to a game B, is going to be a strategy in the compound game given by the dual game of A in parallel with B. And this is following this idea, originally I think due to Conway, and then drawn out and extracted very clearly in the paper by André Joyal. And by the way, when I talk about strategies, I'll always be talking from the point of view of player, so that if I want to talk about a counter strategy or a strategy for opponent, I'll be talking about a strategy for player in the dual game. Okay, so here's an example of a strategy. It's copycat. We've got here, we've got this game A, which is just opponent plays a move, and then player plays a move. It's constrained by this causal relation here. And then copycat is going to be a strategy from the game A to the game A, so it's going to be a game in the dual of A in parallel with A. So here's the dual of A. It looks like that. It looks like the original game, but with a reversal of polarities. And then we want to follow the spirit of copycat. The spirit of copycat says a player does whatever opponent does. So we put in causal constraints like this. So the S part, the actual play, is represented by an event structure which we get by adding these causal relations to the original game. It's not always as simple as that. Sometimes there are many more events in the S part than in the actual game. So that's an example. What's going to drive the definition of strategy is that we want strategies to satisfy enough conditions, or just enough conditions, so that when we compose them with copycat, copycat acts like identity. That's the idea. Well, how do we compose these strategies? Well, there's a lot going on here, but we're going to compose strategies by taking pullback in the category event structures with these total maps. And this is a natural thing to do whenever you're talking about composing two systems which share some common interface. Now, if you look at a strategy going from A to B, looks like that. Strategy going from B to C looks like that. They're not directly amenable to taking pullbacks because they're going to slightly different places. And then there's this business of the polarities getting in the way of it. So let's forget about the polarities for a while and pad out the strategies by appropriately put the strategy sigma in parallel with the game C, and strategy tau in parallel with the game A, so that they go to a common codomain. Then we can take a pullback, and this pullback will have the effect of synchronizing S and T on the common moves, or complementary moves they make in B. But when we do that, we get a pullback, we get something which is actually living over a game which is the composition of A and B and C. And we want just a game of the form A parallel C. So how do we do that? Well, we've got a natural projection here, which is taking all the events in A and C to just by identity, and forgetting and taking B to undefined. Composed with a map we get from pullback, we get a partial map from P to A parallel C. And what we do is we take the defined part of that. We just look at the domain of definition inside P, and we mathematically restrict P to that, and that gives us the composition of strategies. There's a lot going on, but it has a background in synchronizing processes, and it's fairly well tested kind of idea. Okay, but what we want is extra special conditions that we put on non-deterministic plays to make them compose well with respect to copycat. And here's one formulation of them. It's that it says that if we're in a state of play X and it goes to a position in the game sigma X, and from that position you can make purely opponent moves to some position Y, then the strategies should be receptive to that, in the sense that there should be a unique extension of X, necessarily by opponent moves, to X prime, which goes down and is mapped to that position. Okay, so that's a kind of receptivity condition. There's another condition which amounts to saying that the only extra causal constraints that the strategy can make are ones of the form player awaits a move of opponent. So you don't have things, you're not allowed in a strategy to make opponent await your move, for example. And that can be said in this way, that it's a kind of backwards version of this. If you have a state of play X that goes to a position in the game, and you go backwards by purely by player moves to Y, then that's reflected in the strategy by being able to go backwards necessarily by uniquely to a state of play X prime, necessarily just by player moves, which gets you to that position. Okay, and this characterization stared me in the face for a number of months until I realized what it's really saying. And what it's really saying is that strategies, when you put these axioms on to make them compose well with copycat, are really special kinds of pre-sheaves. Now, here, we almost have a kind of pre-sheaf-like condition. We've got this is the conditions for a discrete vibration, which is an equivalent way of expressing pre-sheaves. This is pointing the wrong way, however. But if we do what seems initially like a kind of hack, and we build a new relation by just taking the plus relation in the right direction and the opponent relation in the opposite direction, then turns out we do get a partial order. Call it the Scott order, because it's always the case that you can normalize that. It's going to be a partial order. It's going to be a partial order which is part of a factorization system. You can always normalize it to doing less opponent moves followed by more player moves. And so if you read opponent moves as input and player moves as output, it's very similar, and in fact in special cases amounts to exactly the kind of order that we see on Scott domains for function space. And then lo and behold, although it wasn't immediately obvious to me at the time, this gives us another characterization of the configurations we see of copycat. If you take a configuration of copycat, it splits into two components: the configuration of the dual game of A and the game A, and these are these two projections here, and the configurations are precisely those which are in the Scott relation. And in fact, if we take this relation very seriously, then we can show that strategies are precisely those, in some sense, I'm not going to go into right now, there's not much time, strategies are precisely discrete vibrations, and so precisely pre-sheaves of a certain kind. And this works well also when we talk about not just strategies in a game, but strategies from a game to another game, and it gives us a way of going from strategies to profunctors, but laxly. What happens is that you don't quite preserve composition on the nose, and that's because when you take composition of profunctors, it's like composition of a relation. You're just looking for any old thing that matches in the middle. Okay? Whereas the strategies, I'm speaking rather intuitively, whereas strategies are such that they insist that that thing you reach in the middle has got to be somehow causally reached in a causally secured way. And it tells you how to kind of how to extend your strategies. How to extend your profunctors so they capture exactly strategies. But that's another story I can't go into now. But anyhow, so we've got a bi-category of these distributed games with these distributed strategies, and by the way, it's got a lot of structure. It's a compact closed category, and to hark back to some work that Prakash and I did in the mid-90s with Thomas Hildebrand, there's a automatically a feedback mechanism here, and it coincides with the one that we got. Thank God. But now I'm really concerned, what I'd like to get across is the new stuff, which is adding probability to strategies. So strategy looks like this, And what we want to do is somehow add probabilistic information to S to make this into a probabilistic strategy. So we want to endow this with probability, but at the same time take account of the kind of thing that Gordon was talking about, that we don't know. We don't know what probabilities opponent is intending to assign to his moves. And here I was I checked the idea I had against some earlier ideas of Vincent and Rastan, just to see, gave me confidence when I saw that they were doing essentially the same.
I'm anxious, so is that alright?
I think so. We'll see. So anyhow, first of all, let's look at the simple case of just probabilistic things without any opponent moves around. So here to cut a quite long story very short. I mean, the driving idea is that you want a probabilistic event structure without any opponent moves around to coincide with an event structure on which you've got a continuous valuation on the domain of open sets. Okay? Now, by the nature of continuous valuations, what that means is that the continuous valuation is determined by, the domain looks like this perhaps, and the continuous valuation is determined by the open set, the sub-basic open set, subtended by some finite configuration. Okay, and so the continuous valuations, by the nature of continuous valuations, are determined by their values on such sub-basic open sets, so by the values they give to finite configurations. But what kind of functions do you get from those? And here's the more workable characterization. It's exactly equivalent to that information. Well, there's a lot in here, but it's what it's saying is that the thing you have to be careful of when you do this kind of assignment, that if you have some other things, x1, x2, up to xn here, which are above y, then you've got to be careful that by using you better be careful that the probability you want to assign to this region which is above y and not above any of the x's, that is never gets negative. And that can be said by a kind of, oops, I've gone wrong. I've gone way ahead. Sorry, what's happened? I'm going the wrong way, that's what's happened. Sorry. That's right, that's what I wanted to do. So to get this, to work, the condition is just expressed here. That's saying that these drops that you get in these general intervals have always got to be non-negative. Okay. But how do we generalize this to the situation where we have some opponent moves around? Well, this is this kind of where this works. And now I don't have kind of an external characterization of why this is the right thing to do, but it fits with what Branson and Russ did. It's that you only insist on this drop condition for moves forward which are purely don't contain any opponent moves. And on opponent, if you just extend by opponent moves, then you keep the valuation the same. And that works in some sense. There's a choice going on here, and I guess Gordon is showing that there's a range of choices you might make, but this is one choice that works. Okay, and when you do this, you find you have to restrict games to being race-free games, in which you never get into a position where opponent and player are competing to do their moves. That if you're in a situation where opponent and player can play, they can't block each other. It's not a great restriction. And if you do this, you find that copycat becomes a deterministic strategy, so it's easy to make it probabilistic. You can just assign value 1 to all configurations. And it turns out there's a nice little result, which is showing how to get the drop of a composition in terms of a product of the drops of the components, which guarantees that you inherit the drop condition from the components of the composition. And lo and behold, of course, you get a bicategory now of games with probabilistic strategies. But there's a slight complication which I overlooked in some publications about what the two cells should be, because the two cells had better respect this probabilistic structure that you have. And here, this is what I've come up with, and it works well. and it gives you the kind of enrichments that support recursion, recursive definitions of probabilistic systems. It's that the two cells are going to be like this kind of form. But now, in order to get the probabilistic structure respected, what we do is we insist that such f's reflect plus compatibility in this sense. And if you do that, the drop conditions transfer appropriately, so you can insist that the valuation function associated with sigma is just that got by image under f, the valuation associated with sigma. And this includes then things like rigid embedding, and in particular this kind of concrete way of realizing rigid embeddings in terms of kind of this substructure order. But people know best, I suppose, with information systems, representing Scott domains, but in fact they were first discovered with, in the context of defining event structures recursively, and capture just rigid embeddings in a concrete way. So now we can start looking at a little language. We have a language of strategies, and we can see how it specializes down to a language of probabilistic strategies. And as you might expect, there's some restrictions we have to make every now and again. So the language is a little non-standard, but in order to reflect the kind of duality there is on strategies, I've chosen a kind of two-sided sequent formulation. And we're thinking of terms like this, with variables on both sides, is representing a strategy from this compound game to this compound game, and you can think of it as a box like that. And the idea is that such a term denotes a strategy in this compound game here, and it's describing that term. It will be a term built out of the configuration names x and y, and it will be a term that is describing a configuration as witness to the relation between those x's and y's in the manner of profunctors. Once we've got this in this language, we've got duality. Whoops! You can easily switch backwards and forwards between sides as long as you dualize the game, and you can take composition as well on some common part. And given that you can shift things freely from one side to the other using duality, you could shift everything over to the left here and everything over to the right here, so delta was empty, and then you would amount to just a simple composition of the two strategies seen side by side. But in general, if delta's non-empty, you've got some more complicated synchronizations that are going on and then leave here. Now, here's how the variables can creep into the terms. Think about the term that you could write down for copycat, and if you look at it, if you look at strategies as sometimes super-duper profunctors, this is not a silly thing to do. You want to somehow have, for the identity, you want to have a Homset. Okay, we're talking about partial order categories here. Scott order is a partial order. By the way, if we put symmetry into these games, which we have done, then this partial order becomes a real category, so this becomes a non-trivial category. So this is how we write down copycat. Because of that characterization we have of copycat, copycat is really, a configuration of copycat is really got from a configuration of the two parts with extra causal connections put in. So this thing here is describing the witness of this form, x and y with extra causal links in it. But in general, we might have, oh dear, I keep doing that. In general, we might have more complicated terms on the left and right here with variables in them, and it's useful to get an operations analysis, which we won't be able to talk about, to be able to generalize these, to have these terms so that they denote affine maps of event structures. We can have expressions like X union some non-empty configuration or something like that. And then this construction works in general, and we can write such an expression, and it will make 4 minutes left. Then we can make sense of this as some kind of configuration, which puts in wiring, but somehow respecting the maps f and g. That works in general if we don't have probabilities around, but if we want to have probabilities around, we want to be careful that we can assign probabilities to this. So we can do that if we make sure this this is deterministic, and we can do that, we can make sure it's deterministic if we insist on F reflecting, well, G reflecting plus compatibility, condition we saw before on the two cells, and then F reflecting opponent compatibility, which is a kind of dual notion. And if we do that, we get a deterministic strategy for which we can then assign probability 1 everywhere. This gives us a way of lifting maps to strategies. And this is how, in general, you would lift a map over to a kind of direct image strategy going, which is expressed in this way. Analogously, there's a way of lifting a map to a kind of inverse image strategy going the other way around. And in fact, if we look at this guy here, it rather interestingly is such that if you have a strategy sitting over B and you compose it with F star, or compose F star with it, then what you get is a strategy which is the pullback of the strategy B across the map F. Strategies are closed under pullback under maps. And this, by the way, subsumes prefixing, because what could happen is A could be some prefix version of B, or more complicated than that, and this would introduce for you, these maps would be partial to, this would introduce for you a new prefixing map, a prefixing event sitting underneath the strategy, which would then kind of behave as before once that prefixed event had occurred. There are pullbacks of strategies. To give you strategies, it's a kind of Hoare-like composition. You synchronize the two. This pullback is a strategy which agrees like the kind of is a strategy which is somehow the agreement of the two strategies which you're taking the pullback of. However, I should warn you that I've not managed to show, I've not managed to get the verification that this really is a map. Okay, that works properly. Probabilistic sums, you can take an arbitrary probabilistic sum of strategies. There's also duplication, which you can also assign probabilities to. It's a subtle operation, discovered only relatively recently. The duplication strategy goes from A to A parallel A, and by assigning probabilities in a uniform way, one can get it extended to probabilities, and that gives you a way of doing the equation. Using standard old techniques from about 30 odd years ago. Okay, and finally, what to do? Quantum things, because you just replace the games by quantum event structures. Quantum event structures are event structures in which you assign events to projection unitary operators in such a way that concurrent events go to commuting operators, and then they locally determine probability distributions. And putting this machinery on top of them, you've got a language of strategies which will give you, when you play strategies against counter strategies, will give you a kind of probabilistic quantum experiment over the game. Okay, welcome to 60. It's not as bad as it seems. You can survive. And yeah, that's right. That's slightly worse. Stay young at heart. Okay. Yes.
We talked about signed measures. I was wondering what would happen to your probabilistic event structures if you actually put signed measures and then try to impose conditions that would restrict the observables to having only proper probabilities. That's an interesting thing to explore.
I don't know. When I was very sad to miss his talk, I thought I would just about make it, but I missed it. So I can't say that it's anything specific.
Well, it would be interesting to relate it to your quantum event structures, because that's the context in which
I see. Yes, and that's relatively unexplored, but it's clearly, the language here would fit on top of these quantum things. Okay.
Yeah, just a quick question. Is it a terrible idea? You said that you can laxly map your strategies to per-functors. You wouldn't want to define a strategy to be a per-functor instead. That wouldn't give you what you wanted.
Well, I've done it, you see. I mean, that's what the pre-sheaf models and pro-functors was a kind of generalized domain theory of concurrency. And it sometimes gave nice connections to operational semantics in that the realizers could be connected up to operational semantics, but I couldn't always do it. Now we have an operational semantics where we do get a connection between events and atomic derivations in the operational semantics for a very general language. for this essentially this meta language you've seen here. So yeah, it's not a bad idea, but it's kind of been tried and tested, doesn't quite work. If you want to connect that up with operational.
So you could make non-determinism and probabilistic non-determinism.
Yeah.
So you could do my example.
Yes, I think that's right.
Would there be something to say? I mean, I know
It's
it's a
too
bit
early,
too fast a question.
Well, I hope so, and I think so. I mean, this is kind of fair. The meta language is fairly recent, and then putting probability on is even kind of inspired by wanting to do something new with Prakash. So it's not tested, but I think that would be something to try out. Yeah. Let's talk about
We
it.
need to have a workshop on combining probability and non-determinism.
Yes,
So
once
we-
more.
Yes.
Yes, that's right. Yeah. And it connects up with Mike's work to some extent, because there's some things there that you want to look at.
We keep talking about that.
Yeah, and your remarks maybe to get things right. I got the two cells slightly wrong. Well, wrong enough.